Okay, I'm going to do another video on microcontrollers. If you find that kind of boring, you probably don't want to watch this video. I guess people subscribe and they land on a video and they go, what on earth? Yeah, because sometimes my videos have other stuff in them, including nature shots and that sort of thing. So this project is going to be on another microchip called a PIC12F675. It's a microcontroller, 8-bit microcontroller, and it's quite an old chip. I'm going to use probably something newer in the next videos. This one is 20 years old, way outdated. They still sell them, but there's a point where Microchip will stop selling these chips, and I think it's good that I maybe steer you towards something a year or two old. That way you have another 15 years of learning the same chip. A lot of times, even though this is only like 130 pages, some of these chips, just to learn that much information, you find it frustrating if they discontinue a chip next year and you think, oh my goodness, all that information is lost because they don't transition totally perfectly across from one chip to the other. So, okay, this is the project we want to do. We actually don't want to flash a red light. We're going to make it so this will flash different colors. It's going to flash a blue, a red, and a green. Probably not in that order. I don't know. But yeah, this is one of those LEDs that has 4 legs on it. And what I did is I put a resistor on one of the legs. Is it the cathode? Maybe it is. And with a 1,000 ohm resistor running over to ground. And these 3 pins control the color that comes out of this LED. So this pin right here produces a red, this one produces maybe a green, and this one produces a blue light. And I will be using that in 3 different I/O ports. So I'm going to have 3 outputs on this little LED to make it change different colors. I could have made it actually more interesting where I had the oops, what did I do here? Did I want it to flash green? Probably not. Oh, I probably hot wired this across. Give me a second here, see what I did. Oh yeah, look at that. So yeah, you can see there's going to be some green here. Oh, I shifted. Oh, I see what I did. I shifted everything across one pile of bits. There we go. Yeah, legs all went in the wrong spot. So also in this project, we're going to have an input, a little switch, because I think the last video, I never actually showed you how to put a switch into a 12F675, and we're going to run it on just 3 volts. So in general, the way you build a project, I'm going to explain just a general way people go about building their own projects. If you ever want to go through and build something yourself, maybe invent something, usually you draw a schematic out like this. And you usually, you throw down your chip there, you write down it's a 12F675, whatever it is, and you put the little legs there, 1, 2, 3, 4, 5, 6, 7, 8 legs, and you decide where you want to put your components all around it. So for instance, in this example, I want to put, well, first I want to find where I put my pen. Oh, there it is, right here. So what you want to do, I want to make sure I'm still on the screen here. Okay, good. So these 3 little legs that create the color, I'm going to put them on pin 5, pin 6, and pin 7. They will be output ports, so they can throw a high or a low onto this little LED and make it change colors. Of course, I take the other side. It's through that 1K resistor, goes straight into ground. And oh, by the way, of course, this chip has to be driven by some voltage, so I'm going to put a ground on 8 and a high of 3 volts on pin 1. The switch, as mentioned, will run from pin 2, which is going to be my input port. I'll probably actually make pin 3 and pin 4 inputs as well, just because, I don't know, keep 3 outputs over there and 3 inputs over there, and you'll see how I do that. So anyhow, pin 2 will be an input. It runs right through this switch and runs to ground. So whenever I push the button, that will go to 0, down to clear or low state. But without that button pushed, you can see I've wired a 1K ohm resistor between, well, high and 2. So it's normally, without the button pushed, it's on a high. It'll be sitting at 1 as far as a digitized number. And as soon as I push the button, it goes to low. Yeah, it's nice to draw out a schematic because then you can figure out how you want to build your I/O ports. If you didn't have this right here, you wouldn't know how to start your project. Once you've got this sort of thing drawn out, then you can move towards building your software. What we're going to do here, I'm going to pull this chip off of here, and I'm going to put this into my programmer just so we can kind of get this out of the way. Let me move this over here, and here's my programmer right here. It's actually a Microchip 3, and I think I will buy a Microchip 4 next week. So the Microchip 3 has a header there you can see right here. It's got pin 1 designated with a little triangle, and it's got a header of 6 little outputs, and I'm actually only using 5. You only use 5 actually. And the way it works is you wire it up this way. I've actually written down the instructions from the website. So for instance, Microchip 3, pin out 1, which is that blue line, will go over to PIC 12F675 pin 4, which is that pin right there. So the pins are actually 1, 2, 3, 4, 5, 6, 7, 8. So yeah, I've obviously plugged that one into that one. You go all the way down the line, you know, pin 2, which is that red wire, goes over to this chip number 1 pin, all the way down, and you have that for that chip right there. By the way, another way to look at this as well is you can see I've got my LED that will be on these 3 pins right here, and they are actually GP0, GP1, and GP2. I'm going to be putting my my switch, my push button, on this one right here, number 2, and that's called GP5. So when I start saying I'm doing something to GP5 or GP2 or GP1 or GP0, you'll know that I'm referring to those little pins right there. Anyhow, let me put this right into my USB port that's powered into my Windows 10 based computer. So I'm just going to show you a few things, maybe a bit more detail than the last video I did. Okay, so this is the way Microchip tries to organize all of its file registers. It has 2 banks, bank 0 and bank 1. And you can move between bank 0 and bank 1 by flicking on or flicking off a bit in register 3. So when you go over to the status register, as they call it, register 3, bit 5. Let me show you right here actually. Yeah, you can see this is the status register. This is more, by the way, this is bank 0, and this is bank 1. This is just more information on 0. And this, of course, will be more information on bank 1. But if you go over to bank 0, let's say, register 3, the status register, this one right here, bit 5, is the one that if you set or clear, will shift between the banks. And actually, you can get more detail on that just right here. The status register, which is register 3, bit 5. Obviously, if you set it to a 1, it'll run over to bank 1. If you set it to a 0, you go over to bank 0. So that's how we're going to get around the banks or move through the banks, and that's normal. So in general, we are going to start off our program, and we're going to change a few things that we never changed before. We're going to run over to bank 1 right away, and we're going to, what do we want to do? Let me peek at my cheat sheet here. What we want to do is we want to number 1, we want to go over to the analog select bit right here, or byte actually, way down here at 9F, but really that's actually 1F. Disregard all of these numbers here. They mean nothing in the way I program. Okay, use this right here. It's 1F. So 1F in bank 1 is where we want to go. The analog select bit. So we go over here. They tell you a little bit more information here. Analog select bit. What we want to do is we want to turn all these little pins into analog made into digital I/O ports instead of analog ports because it comes from the factory set up as an analog chip. More information is on page 44. Let's run over there right now and have a look at what I'm talking about. Okay, so you can see right here, analog select bits 0, 1, 2, 3, right there. You can see it says on these four right here, you can select it to be an analog input with a 1 on that register. And as you can see, it comes from the factory set for a 1, or it's already set for analog. I want to switch those things off because if you set it to 0, it becomes a digital I/O port. So that would be 0 all across there. Matter of fact, everything would be 0. So I'm just going to clear file register 9 or 1F to solve that problem. Now we run over to okay, so yeah, we did that. So what I want to do over there too as well, while I'm in on bank 1, I want to run over and change my I/O control or my input-output control, so I can designate any one of those pins to be either an input or an output. Well, except for IO3 actually. I'm going to designate them to be, where are we here? So on register 5, on bank 1, which is right here, this is bank 1, register 5, I want to do, maybe these 3 will be outputs and these 3 will be inputs. So the way you do that, so I said these 3 are going to be outputs. Output will be a 0 because zeros represent when things are going to be outputs and 1s represent when the pin is going to be an input. And as you can see here, in binary, that's actually 3 and that's actually an 8. That equals 3, 8, right? So I'm going to be putting a 38 into register 5 in order to make these this I/O port function this way. So we have 3 inputs and 3 outputs. So that's register 5. I'm going to throw a 38 into there. And then I'm going to go back to bank 0 by using the status register. I'm going to set it to 0 or clear it. And then I'll be over in this register, this bank of registers here, and I want to change the what is this called again? This is the comparator control register. The comparator control register tells you or tells the processor whether you want the comparators to run or not. And they are actually, it's a single comparator. It's actually on from the factory. I want to turn it off because it saves power. So down here, number 19 on bank 0, I can see I can get more information by going to page 35. So we run over to page 35. Oh, look at that. It landed right on 35. And as you can see, there's a little bit of information there, a little bit of information here. And it tells you how you can set up your comparators so you can turn them right off. All you have to do is set the least significant bits as 1, 1, 1. Okay. So I will go along and I'll set these 3 right here, the least significant bits, to 1, 1, 1. And the rest are 0 anyhow, so I can just go like this. And I can see that number I want to put into that register will be 07. So I'm going to throw a 07 into address 19, or file register 19. And that way it will turn off your comparators and save a little bit of electricity, which is what we really want to do, right? What else can I tell you? Probably been doing a lot of talking without any details. In general, this chip here has 1,024 bytes of memory, program memory actually. So what that means is you can write, well actually bytes, I mean words. You can write 1,024 instructions because each instruction takes 1 word of memory. The static RAM, you have 64 bytes that you can work with, and 64 is basically, is it really 64? I guess it is. That's not very much. So there's 64 bytes of RAM, and that's the stuff that when you unpower your chip, that is lost, and it starts back from factory when you turn it back on. Whereas the memory stays in always, even when you pull the chip from the power source. And same true with EEPROM. Double EEPROM will be permanent. Well, not permanent. It'll stay without the battery, but you can change that on the fly. It's a little bit more complicated to change double EEPROM memory than it is to change SRAM or static RAM. The advantage of static RAM is it's very fast, very easy to change. You just simply request to put a number into a register and it goes in there and it's stored. Whereas this one, it's much more involved, but it will be permanent until you change it again. So you can change, for instance, double EEPROM a million times. If you had things you wanted to stick in there and remove and change and alter, you can do that a million times. Out of curiosity, your flash memory, you can rewrite your program and stick it into that chip 100,000 times. So you'll never do that. I mean, my chips probably don't see more than a dozen times just from a dozen different programs. Is that all that I want to explain to you about this manual? Yeah, obviously, maybe I'll go in a little bit more detail in the programming part. So this is, again, a very simple style of programming. It uses, what do we have here? That was it. I think I have like 8 pages. I don't know. Not very much for the programming. So the programming language is all in these 8 pages. Matter of fact, it's only 35 pieces of, or 35 instructions. And the way this is read is that's your instruction, the mnemonic going down there. And this tells you more detail of what that mnemonic means, such as add WF means you're going to add a W, a working register, and a file register together. And what that D will mean is the direction or where the answer will be placed. Either if you put a 0, it's going to be placed in the W register, or it's going to be placed in the file register if you have a 1. And I think it actually says that right down here in this section here. But yeah, you have to read this over very carefully to know exactly what's happening here. So for instance, bit clear file register. That's what it says right there, bit clear file register. So what it'll do is it'll come along and it will clear the bit of that file register in detail. It goes like this. You can put a label in the front if you want, and then you type out BCF, then a space. I usually use a tab, and you have a file register next, and then a comma, and then the bit number you're going to clear. Which basically what they're saying here is your F, your file register, can be anywhere from 0 to 127. Your bit can be anywhere from 0 to 7. The operation basically is putting a 0 into the bit of the file register. No big surprise. Yeah, so that's how that works. Like I said, this here instruction set, there's more detail in the following pages of how to do each one of the instructions. And with 35 instructions, a very simplistic programming language. The disadvantage is you don't actually have a multiplication or division instruction. You actually have to create it if you really want to multiply something. And if you know anything about this style of coding, you actually create multiplication by using a string of instructions that will roughly shift a register and add. Because shifting binary and adding it actually multiplies it. I know, it's weird. But yeah, what else? Yeah, and even if you wanted to move a number into a register, it's not actually that simple. You actually have to move it into the working register first with a command like move. Where's the move? Move a literal, a number. You can pick a number. Move a literal into a working register, this command right here, and then you move that working register into a file register. So it took 2 commands or 2 instructions to actually move the number you wanted into the file register you wanted. But nice thing is, each instruction, it's only 1 machine cycle, and there's only 2 machine cycles. So In the case we're going to be running a 4 megahertz clock, that roughly works out to 1/1,000,000th of a second for every instruction. So it takes 2 instructions to do what we just talked about, which is 2/1,000,000ths of a second. What are we going to do here? Let's, oh yeah, did I mention that I did remove the battery pack, and we're going to actually, I'll show you how to run this without the, I think I did, without the battery pack to program that chip. Hopefully I might have mentioned it, but we'll just see. Let's get this up here and let's see how this is going to look. Okay, so what I'm doing here is so archaic and so redneck that I'm sure it drives some people crazy. It drives me crazy. It should drive you crazy too. Okay, so what do we have here? We have a Windows 10 based Microsoft computer, whatever. So that's, I'm using actually a new piece of software. I'm using MPLAB XIDE 5.35. Actually, I like it because I can get a few more pieces of, a few more types of processors that I can use from Microchip. And as you get higher up in these numbers, like 5.35, if you go to 7, you'll find that it will not be all that easy to run assembler. They actually do probably want you to migrate towards C. So if you want to learn the C compiler, you go ahead. But I just thought it so much simpler to work this. And if we stay back at 5.35, there's still brand new current 2022 chips we can run in that old compiler from 2 years ago, I guess. And anyhow, double click on it. We'll see how this one rolls. I just recently got this, so I think we'll see how it works. So anyhow, clearing everything out. Just let me clear everything out. That looks nice. Goodbye. So let's start, and we will set up our program. We go in here and we get a project going. So new project, click on that, and we want to do a standalone project. Click on that. Go to the next. And we want to, what chip were we using? I think it was a 12F675 today. But yeah, we'll be using something newer. I'm going to try using something like maybe a year or 2 old chip that we'll program. Keep it small as well. Maybe I'll bring it up in size, bring it up to maybe a 14 leg or 16 leg chip. So it'll have a lot more potential, and we'll learn some programming on that. Anyhow, this is what we got, the little 12F675, and we go next. And we don't actually need a header for this program. There's my little red Kit 3, and I will go next. And I think I'll use the most advanced or the best assembler right here. Is a 5.87, and that's what came with this piece of software or this download. Next. Okay, so I need a project name. I'm going to use test something. Test, I don't know, 124 maybe? I don't know. Okay, so that's good. And now there's test 124. And I'm going to go to the source files. Actually, let me just close a few things out, so it looks a little bit more controlled. Source file. I'm going to left click, right click, and grab a new simple ASM file right there. Now, file name will be, what was that? Test 124 or something? I don't know. Yeah, it is. Great. Finish. Okay, and oh, there's some junk on this. I'm just going to erase all this right here. Nice. Okay, so first thing we do when we program these chips is we do have to explain how this chip is going to run, whether we want it to have an internal or external oscillator, whether we want to lock our data coding up so nobody can steal it or not. So what we've got to do is got to go over to production, go down to set configuration bits, and we have them right here. So the first choice is how you want your oscillator to run. Is it going to be an external oscillator, RC oscillator, or is it going to be an internal oscillator, or is it going to be crystal controlled, or whatever? These ones are usually crystal controlled, and it can be anywhere from a low powered one all the way up to about a 20 megahertz crystal. But we're going to use an internal oscillator just so we have maximum number of pins to be used for I/O port. And that's that one right there. And we're going to turn off everything else because it's not really essential on this program. So we turn off the watchdog timer, we turn off the memory clear feature, the brownout detection. Yeah, so they do a variety of things. You might want to read up on them. They might be useful. But code protection, just basically so nobody can steal your code. If you come up with a great invention and you don't want anybody to figure out how you programmed your coding, you code protect it here if you wanted to, or you even code protect your data. You don't really need to in this particular job because I already know what you're going to type. So anyhow, generate your source code right here. Click on that button, and that stuff there, and I only need really this much of it. The rest are remarks. You can tell by the little semicolon in the front that it's a remark, and it's only somebody like you that needs to see it. Anyhow, I'm going to copy this and paste it at the top of my program. So I put it as a header here, paste it right there. And really, like I said, these are remarks right here. I don't need these remarks. I can pull them out if I want, just like that, and they're gone. Like that. Matter of fact, you have a lot of control of what you want to do here. So the only other thing I do here is I type out where the origin of the code will lay in my chip, and it's going to start off at bank or address 00. And now we're ready to type out code. So I try to keep it really simple. You can see there's only 3 lines of directives or whatever for the compiler to have to read. And after that, it's your own code going in there. So I'm going to start typing out some code, and I'm not really great at conversing and typing simultaneously. So I'm going to type a little bit, and then we'll talk a little bit. How's that sound? So bear with me. So what I've done here, these are actually your first 3 true lines of your code that you're typing out, okay? So what you've done is you've taken the number 7, you've moved it into working register right here. So the instruction says move a literal, which is 7, number 7, into a working register, and that's what it did right there. And then right here it says move W, which is the working register, into your file register number 19. So now we've just put 7 into number 19. That's kind of handy. I guess that's still, I have to glance at my screen, make sure everything's still in the right spots. Okay, so you've got a 7 into bank number 19, or file register 19. And if you remember from what I said, file register 19, I was going to turn the comparators off. So they saved a little bit of power. You don't have to do it, but I generally do. Bit set file register is 035. Now that will bank over to bank number 1. I was just previously in bank 0, and now we're in 1, and we're going to do some more coding now. Give me a second here. Okay, so I've run over to bank bit set file, bank 1, And first thing I did is I cleared file register 1F. Hey, actually, curiosity, you see that F, it's a different color? That's because the compiler isn't quite sure. It's very used to having numbers down this section here. And it's just aware there's something funny, not sure. Yeah, honestly, it won't be a problem because it'll know that hexadecimal is the number system we usually work in. So there's not really a problem. You don't have to do this. You can if you want, but you put a OX in front, which designates that number as a hexadecimal for sure. Okay. It will naturally assume it's probably hexadecimal anyhow. But anyhow, you're doing that keeps all the code on one side black. And if you like building code that's easy to figure out, you usually try and make everything more uniform. You know, it's all blue over here and black over here. Little things that could go wrong. For instance, let's say down here, maybe I typed in an O instead of a 0. Well, it's going to show up. And you'll say, wow, look, I can spot that problem really quickly without having to do too much. Whereas normally you'd think, oh, what's wrong with an O instead of a 0? Well, that's not really a number, right? That is a number. So having your code black on one side and blue on the other side helps spot errors before you even try and crunch your code or put it through the compiler. Anyhow, moving on, clear file register 1F. That one cleared up the comparators, turned them all off actually. Move literal into the working register. This 38 is the number we were going to use to designate how the I/O control was going to work, or how the I/O pins were going to be put together. So we have some output and some input. So again, that number, what is that? That's in binary. That's isn't that something like about like that? That's that binary number there is equal to 38, right? So the least significant bit here, it's going to be 0, 0, 0, which represents 3 outputs, because a 0 represents an output and a 1 represents an input when it's installed into file register 5. So anyhow, file register 5 right here is where it's going to go. It says move the working register into file register 5. Here, I'll get rid of this. Yeah, I'll get rid of this. Putting that number into file register 5 will create the I/O port the way we want it. And now that was in bank 1. I'm going to go now back to bank 0 by going bit clear file register 03 bit 5. So now I'm back in bank 0, and I'm going to continue on in my little typing spree here. Matter of fact, I'm going to add my first label here. By the way, you don't have to call it start. It's not really the start, is it? This is the start up here. That's the start of the program. I'm just calling it start because I could call it anything I wanted. So, start. Give me a second here. That's about it. Okay, good. So what that does, this is a trap. What we do is, this here is actually waiting for the push button to be pushed. So while it's waiting, it's going around in circles. Because if you look at this, where is that thing? So bit test file register, skip if it's clear. So the only way it's going to get from here past this instruction is to have bit 5 on register 5 clear. So while it's set or on a high, it will continuously do loops. Okay, so bit 5, register 5, when it's high, this is going around in circles forever until all of a sudden it sees a low. So it says bit test file, skip the next instruction if it's a clear, and if bit 5 on register 5 is a low, it'll skip over to here. Kind of cool, eh? So that's how we trap the program waiting for something to happen, like an event, such as a push button. And we're going to go down here and we're going to do something. So now we're going to do our real program, which is to make the lights go on and off. So what I'm going to do is type for a while. and not talk. Yeah, I guess that's very short. Okay, so bit set file register 050. So what I've just done is I've just set register 5 bit 0. I've just turned on the light, right? That's a set command. And then I've run over to call a delay so that because these processors work so quickly, if I was to set that and then move on to the next light, it'd be so quick, it'd be a millionth of a second. You would not actually see the light come on. It'd be a blur of nothing. So down here, I'm going to build my delay actually right now. So here's the delay routine. Yeah, so give me a second here and I'll just do a little bit of typing here. And you can probably figure out what I'm doing probably. Where am I going to put? Maybe in 22. I don't know. So what I'm going to do here, the way it works is I set a light right here. I turned on a light, bit set file register 5, bit 0. Turned on probably the red light, I think. And then I call a delay. It's run down to the label delay, and it's going to start right here again. So basically, this says move the literal 0A into the working register. And then, of course, move the working register into file register 22. It won't make any sense until I'm finished here, but you'll see. Then it drops down to the next line, and it says decrement file register, skip if 0, 20. So it's actually going to decrement file register 20, and it's going to skip if that file register turns out to be the answer is 0. But it's not going to, because as you're decrementing a register, it actually runs through, I believe, a 8-bit byte or 8-bit register will take 256 decrements before it goes to 0. The one just merely says that it's going to put the answer of the decrement back into register 20. If that is a 0, it'd put the answer into a working register, but it's not. So it's going to go around and then go to a loop. Of course, means go right back to this label here. So it's going to go around in circles roughly exactly 256 times until finally it goes to 0. The answer is 0 on the decrement, and it will finally skip over here to here. Yeah, out of curiosity, there's a 4 megahertz clock in here, which means there's a 1 million instructions per second, or 1 millionth of a second for every instruction. And each one of these loops takes actually 3 instructions. It goes 1, 2, 3, 1, 2, 3. So 3 times 256, that little loop will take 756 microseconds, I believe, to fulfill. Still, I need to do more loops because that's too fast. I'm going to try and slow this processor down even a bit more. So give me a bit of time here to try and slow this guy down. Returning, I guess is good. Okay, so what this is doing now is basically it's called a nested loop. So you do a loop here for 256 times, drop down, decrement this 1, and then go back up and do this all over again 256 times. Do this one more, go back up here, and it will continue to do this whole thing, and then go down here. Of course, I've set this one up so it's actually got a value of 0A. You see right here, move leader into W, W into followers to 22. That's going to basically put an A into here, which basically it's 10. So it'll do this about 10 times, creating roughly 3 seconds maybe. And then finally, when it's finished doing all these loops of useless math, it will go, whoops, it will return back from where it came from, which is right here. It will pop that number off the stack, as they say. So then when it gets back to here, I will, well, I want to turn off that red light and put on the blue light. So I will bit clear file register 050. I'll turn off that red light, and I'm going to now bit set, turn on the other light. And of course, I will call another delay because you want to see what you're doing there. And then when it comes back from the delay again, I will turn off that blue light. By doing that, clearing it. And then I will turn on the other one. Which one was it? I think it might have been green. Maybe. Bit set file register. Yeah, and then I'll call a delay again. There's actually a lot of different ways to build this program. And it'd be really neat, to hear you guys having said, I found a faster way. And there is lots of faster ways to do this. But, if I make it really simplistic, you can understand what's happening here. I'm going to now turn off that green light. And then I will go back to start. And it will repeat that again. Yeah, if you want, you could even try some other ways to make this whole light system work. You could just put a single bit lit and shift it along with a right shift command or something like that. Or you could actually get several colors out of this, because you could have multiple lights on at the same time, and you can just use something to up count a number and tossing it into those registers if you wanted. There's a variety of things you can do. Okay, so that's pretty much the whole code. The whole thing's done. I just have to always remember, oops, not there. Always remember to put an end statement. If you forget the end statement, this program will not compile. So let me just close that up. You don't have to, by the way. You can just leave it as is. What do we got here? So that's the program right there. So that was about, I guess it was 28 pieces of code. Oh, really 28? Yeah, I guess so. That is good. Is that done right? I think that looks pretty good. We're gonna now, and you could reduce this a lot, but I made it as simplistic as possible. So we're gonna build the code and see how it compiles. We've got our little build successful thing. That's great. Now what we want to do, remember I told you I pulled the batteries off the bottom of that programmer? We're gonna actually, before we put it into the chip, I have to put 5 volts into that chip. So the way you put 5 volts into the chip is you go to File, you go down to Project Properties here. Then you run over to Pick Kit 3 here. Run over to this thing here and pull down and find the power thing here. And once you got it, I want 5 volts put onto that programmer. So, and if I had a low power device, which I use sometimes, I would select something like a 3.3 volt or whatever it is, but we're going to use 5 volts. So now I've got 5 volts power on my programmer. I'm going to apply that and okay. So now when I program it with this typical little button here, it will program the chip with 5 volts from USB port. Oh, it's just asking me if I have 5 volts, 5 volt device or a 3.3 device. It should know. So down here, I'm just watching this. Programming, verify. When you actually use this for the first time, you'll find that the chip, it'll take a long time to program because it's actually downloading files for that thing, well, for that compiler to use. So let me just pull this down here so we can see what we've got. right about here, I guess. Okay, so it's now programmed, and I'm going to just pull. I don't have to pull it off that, but I do have to take this chip out of here and bring my project over here like this and put this in here somewhere. So bear with me for 1 second. Maybe I'll put, give me a second here. Okay, so you can see it's kind of working here. So when I push this button here, so it's basically staying still. When I push this button here, it runs through all three. And the button is obviously holding, like I say, the gate. And when I push the button, it runs through the rest of the program. Okay, so probably we'll use a different chip. I was going to do a couple more projects with this, but like I said, the chip is so old, I can do all the projects on a more current chip, and they probably take roughly the same number of pieces of code. So it's not like you're inundated with a lot of code. All you're inundated with is 700 pages of programming information, but you won't use all of it because obviously some of the information is not relevant to you because you're probably not into like a serial programming or who knows what. Anyhow, thank you very much. I hope you enjoyed that, and subscribe, please.